Okay, well, thank you very much for the invitation to this wonderful meeting to celebrate this great effect anniversary. And I will try to talk about how this effect extends beyond the usual laboratory environment and can play some very important role in black hole physics. And in particular, can also play some important role. Should I put this microphone on? It's okay. In probing, possibly probing the short distance physics in laboratory experiments. Okay. So this is the outline of my talk. I will discuss, remind you a couple of things from black hole usual story that black holes do not carry hair, and then how the Aharonov-Bohm type hair can play an important role. And then I'll discuss implications for tabletop experiments and maybe even LHC. So there is the quantum Aharonov-Bohm hair for black holes was historically was discovered in this paper by Krause and Wilczek. But what I will talk about will be a little bit different, complementary. They were talking about ZN quantum hair of black holes. Anyway, so let me just, everybody knows this very well, that black holes are classical solutions, strongly gravitating objects. And the escape velocity, for whom escape velocity at a certain distance exceeds the speed of light. So they are, classically, they are absolutely black. But quantum mechanically, they evaporate, so-called Hawking radiation, with temperature inverse R. Actually, there was a discussion of this yesterday evening. Now, the black holes, they have this very important property that we call, sometimes we call it no-hair, black hole no-hair theorems, which tells you that black holes can only be characterized by the quantum numbers, which you can measure at infinity, okay? So basically, let's say if I take this laptop and I collapse it into a black hole, of course it will be tiny, but it doesn't matter. It still will be a pretty classical black hole. And after a certain finite time, there will be no way to distinguish this black hole from any other formed in any other way, as long as the masses and an electric charge and the angular momentum are the same, okay? So in other words, there are no quantum numbers. So this laptop carries huge baryon number. But the moment it becomes a black hole, that memory is gone. So black holes have no memory where they come from. The only memory about their origin is encoded in their quantum numbers that are associated with massless gauge fields. So things that you can measure at infinity. So this is the classical story. Okay? So for instance, as I said, these good quantum numbers are the electric charge, and momentum, and the spin, and the electric mass, and the electric charge. Okay? So on the other hand, if there is suppose now you have a gauge field or a messenger of an interaction, which is massive, okay? So ordinarily, there will be a charge associated, something like a charge associated with this messenger. For instance, imagine that photon has a small mass, okay? So normally, if photon has a mass and the Compton wavelength of a photon is the galactic size, in laboratory measurements, you will not notice any difference. So the charged particles still will create a Coulomb electric field, and you can measure it, okay? But that's not true for a black hole, okay? So black holes cannot have an electric field, electric hair, if photon has even a tiny charge, okay? So if a photon had a mass, then the charged black holes, the stationary black holes, would not exist. So this is so-called no-hair story, that the black holes do not carry hair under massive gauge fields. Okay. So for instance, if you have a spin-2, if you have a particle, let's say, which is charged under some spin-2 field, and you throw it into a black hole, this spin-2 hair disappears after finite time. So this was proven by Bekenstein, and so the proof is pretty robust. Now, I will focus, so what I will take just as an example, because I want to illustrate how the Aharonov-Bohm quantum hair avoids this classical no-hair theorem. So to illustrate this point, I will choose a spin-2 gauge field, but you can generalize it to an arbitrary one, okay? So Now, this is so in particular, this was the original proof by Wittgenstein in, about the quantum spin 2 pair. So now this is a theory. Yeah, I don't think this works in this way. Anyway, so this is a theory of a massive spin 2 field, and it's unique at the linear level. Okay, so at the linear level, there's a unique theory that exists, the so-called Pauli-Fierz theory of massive spin 2, and so what happens is this. There are two terms. The first term is the linearized Einstein. Oh, thank you very much. So the first term is the linearized Einstein term, okay? And the second term is the massive term. So if I exclude this massive term, this would be simply Einstein gravity, okay? It's just graviton. So now suppose you have a mass. So if, of course, if you have a massless spin 2 state, then you can measure its field. It's just the mass of a black hole. So now suppose this field has a mass, okay? So then the point is that for m equals 0, there is a gauge invariance, okay, because you can shift. This is just the generalization of the usual electrodynamics gauge invariance for the Maxwell field. So you can shift the spin 2 by a derivative of a vector, okay? But naively, for m equals m non-zero, there is no gauge invariance, naively. So h mu nu is physically observable, okay? It's physically observable. And therefore must vanish outside the horizon, and therefore it has to vanish everywhere. So now the point is, which is very important, that so again, as of course as you know very well, the Aharonov-Bohm effect is about gauge invariance. Okay, and when we talk about gauge invariance, a priori it makes no sense unless we specify degrees of freedom that transform under it. Okay, so now the point is that gauge theories, this is very important to understand, that gauge theories, even when the gauge field has a mass, they continue to be gauge invariant. Because gauge invariance is not a symmetry of nature, actually it's a redundancy of our description. And this redundancy is there anyway. So the point is, so for instance, if photon had a mass, the theory would still be gauge invariant. Why? Because photon would acquire a new longitudinal degree of freedom, and the gauge transformations of the two would compensate each other. Okay? So there is exactly the same true for massive spin 2. So in other words, if I have a massless state, like massless spin 2 is Einstein's graviton. Okay? Graviton has two physical degrees of freedom, two polarizations. Okay? A gravitational wave has two polarizations. Now the point is that the moment you put a non-zero mass for a spin 2, this is no longer a same state. You are changing discontinuously your theory. So you are adding 3 more degrees of freedom. Okay? So now it has 5 degrees of freedom. And of course, now if you want to talk about gauge invariance, you have to look closely how these 5 degrees of freedom transform. And that's the whole point. The point is that adding mass to a spin 2 doesn't kill gauge invariance. Theory continues to be gauge invariant because this gauge transformation of 2 degrees of freedom is exactly compensated by the 3 new degrees of freedom. Okay? So in other words, you can write down, this is the useful form, we can write down the massive spin 2 in terms of a massless one, this h hat, this would be normal Einsteinian graviton, plus a vector. And what happens is that the gauge, obviously this theory now is gauge invariant. Everybody will agree with me because there is a gauge shift of h mu nu hat under a derivative of a vector, and this is exactly compensated by the shift of a vector. Okay? So theory is perfectly gauge invariant. Sometimes people call this a Stuckelberg language, but this is not a language. This is the physics of the massive gauge field. Okay, period. So now the point is this. Okay, now I want to avoid. So now the question is, once we realize that theory is hiddenly gauge invariant, how we avoid this no here story about black holes? Okay, and the point is now let's make a parallel with the normal Aharonov-Bohm effect. Okay. By the way, let me remind you that the Aharonov-Bohm effect would continue to be exactly as it is, even if photon had a mass. Aharonov-Bohm effect is completely insensitive to the mass of a photon. Okay? Why? Because the configuration of the gauge field outside the solenoid is pure gauge, anyway. Okay? So what we want to see whether this theory has a locally pure gauge configuration, which, however, is topologically non-trivial, and you cannot remove it. Okay? Now, in the case of a normal Aharonov-Bohm consideration, it's a solenoid, right? And we're looking for something which is topologically non-trivial in a circle, okay? Now, for a black hole is like a spherical object. It's a point-like object. So if we want to have something topologically non-trivial, we have to look for something which is which corresponds to a sphere, which is an unremovable sphere, okay? And the answer is yes, there is such a configuration, trivially, and you agree with me that these equations, they have trivially the solution when the vector component of the spin 2, this A, has a configuration of a Dirac's magnetic monopole, okay? And correspondingly, H hat that also has similar configuration. It's just simply a symmetric derivative of A. And they both vanish. So in other words, the physical field, H mu nu, which you can probe classically, the physical degree of freedom, the physical field, is identically 0 everywhere in the vacuum. But there is a non-trivial topology because there is a configuration which looks like a Dirac magnetic monopole, okay? Now, you should not get confused. I call it a Dirac magnetic monopole simply because of the configuration. There is no magnetic field anywhere. This has nothing to do with Dirac's monopole. It's just this is a longitudinal vector component of a spin 2 field. Okay. So basically in components you can write it in this way explicitly. Okay. So there is this configuration. Again, anything that you could measure classically outside the origin is identically 0. At every given point, field is identically 0, classical field. But there is a quantum non-trivial effect, as we shall see. Okay? So, as you know, you can formulate this trivially in terms of Wu and Yang without any reference to the Dirac string, or you can formulate it with a Dirac string, just as an usual magnetic monopole. It's trivial that in this case, Dirac string is unobservable. Again, it's unobservable trivially. Why? Because there are no particles which are charged, electromagnetically charged under this A mu. Because A mu is a component of the spin 2. And so there is no Dirac string is unobservable. So it's a perfectly well-defined, non-singular superposition, configuration, okay? Which is, of course, it's singular at the origin, as it should be, because it's a black hole. But outside, it's a pure gauge configuration. So now the question is, how can we probe this? Okay, and the answer is we can probe this by Aharonov-Bohm effect, literally. Now, of course, generically, this will not be an electromagnetic Aharonov-Bohm effect. It will be an Aharonov-Bohm effect of corresponding of this. The solenoid you have to make, which should be pretty special. But we'll go to the electromagnetic case in a second. So now, what is the story here? The story is you can probe this configuration, okay, this pure gauge configuration globally by global experiment, by topological non-trivial experiment, if you have a solenoid. Just exactly as in this case of the Aharonov-Bohm case, you need a solenoid. Now, the role of the solenoid in this case is played by anything that looks like a string. Okay. After all, what is the solenoid? If you take a solenoid that looks from the large distance, it's just a string. Okay. It's a magnetic flux which is localized, trapped into a tube. Okay. It's a flux tube. So if you have a string which couples to F mu nu through this interaction, okay, then you can perform an usual Aharonov-Bohm experiment and detect this flux, detect the magnetic, the quantum Aharonov-Bohm hair of a black hole. So what is this experiment? So this is the string, which so x mu, x nu are simply coordinates on the string wall sheet, right? So if I have great thing about physics is that any string from large distances, whether this is a superstring or a cosmic string or a solenoid in your lab with a flux tube, from large distances, it has exactly the same action. Okay, what is the string has just one characteristic. It has a length and it has a tension. Okay, that's nothing else. So the only characteristics of the string is the surface that it sweeps. When it moves in the space, it sweeps the surface. So there are coordinates on this surface, x coordinates x, and that's it. So this interaction is unique. Whether you are considering a solenoid or you are considering a superstring, this is the only large distance interaction you can write down between F mu nu and your string. Okay? So if you have this interaction, then what happens? So now I have this string, and I have a black hole which carries this configuration that I described. Okay, so what happens? If you consider the following scattering experiments, when either you take a black hole around through the string loop, or you lasso a string on a black hole, doesn't matter. Okay, you get a phase shift, and this is literally the same Aharonov-Bohm phase shift. Why? Because when I sweep, so this is the process, right? So you consider the following process: you have a black hole, you are taking the string loop, and the string loop lassos this black hole, and again disappears. Okay. So now in this case you have a phase shift because the change of the action is exactly the magnetic flux of this magnetic flux in a quote unquote, the flux of this F nu, the one that we had before, this flux coming from the string, from the black hole, through the surface that is swapped by the string. Okay, and so this is exactly the what we got here is precisely the Aharonov-Bohm type phase shift. So Q is this coupling to this string. Okay, the string is red, and mu is the mu is the Aharonov-Bohm hair of a black hole. Now, of course, mu we don't know what it is. I just demonstrated that you can have consistent solutions with arbitrary mu. Mu is a parameter of a fundamental theory. We don't know what it is. Okay. Now, in other words, the point is the following: that whenever you have a massive gauge field, spin 1, spin 2, arbitrary spin, hiddenly, your theory contains a topological coupling. Okay? It's like a theta term in QCD. And this topological coupling, classically, it plays absolutely no role because it's a boundary term. But quantum mechanically, it gives you Aharonov-Bohm shift when you do the scattering experiment on a given black hole. And so it gives you, and it's always detectable if this condition is satisfied. This is usual Aharonov-Bohm condition for the relation between the charge and. So now you can ask the following thing. Okay, fine. It's great if you have a black hole which in principle has the detectable hair. This is great, but what this has to do with tabletop experiments? Okay. Now, of course, if black hole carries hair under some exotica, so that I need a superstring to do the scattering experiment, I can detect it, but it's very hard to do, right? The 1 centimeter of the superstring length has the mass of a comet, approximately. So obviously, that's a very costly experiment to do. So you need something more conventional. So the point is this, right? That in fact, you will get exactly this effect, which is measurable now by the usual Aharonov-Bohm effect, by usual solenoid, if you replace this coupling, this term, by the following boundary term, in which this longitudinal component, this gauge field of the spin 2, is coupled to the normal electrodynamics, F nu. So now this is normal Maxwellian electrodynamics. Now suppose you have this term in your action. In the other words, so you replace this guy with this other guy, okay? So, and the question is, what happens in this case? So what's the effect of this term? In fact, the effect of this term is exactly the same as what I said, but now you can use for the measurement the normal solenoid in your laboratory, okay? Why? Because the point is this. This term tells you that if in the limit in which the solenoid, if I'm doing my experiment at distances much larger than the width of the solenoid, as I told you, there is absolutely no difference whether you are dealing with the solenoid or a cosmic string or a superstring. Because again, everybody has the same characteristics. It's a flux tube, which has one characteristic, the length, and the one effective constant, which parameterizes the flux, how much flux is flowing through this solenoid, period. So this is the flux. So in other words, this coupling, this term, simply reduces to exactly the string type coupling. Because after all, there is no difference whether if you have a black hole and you are lassoing it, there is absolutely no difference whether you lasso it by a fundamental superstring or you lasso it by a solenoid made in your lab. The effect is exactly the same, okay? And that's after all, this is the demonstration of the same fact that you can also think about fundamental superstrings as tiny, very, very, very small width flux tubes, okay? And there is absolutely from this point of view, there is no difference between them and any other solenoid, okay? And this is the great thing, because now what happens is that, as we said, so normal Aharonov-Bohm effect is what? How you measure it in the lab. You have a solenoid, so this is red flux solenoid, right? And you have a particle. charged particle, and you take it around, okay? Now, or a black hole, doesn't matter. So you take it around. So now what happens is that you do exactly the same thing here. This coupling effectively in the limit in which you do your experiment, the distance is much larger than the solenoid width, which is true anyway, becomes simply this action. So it's exactly the same thing. And so you get a phase shift. So you get a phase shift of this form. Again, it's the usual Aharonov-Bohm phase shift. Phi times this mu, where mu is this quantum hair of a black hole. So now the point is this, right? So this is interesting because of the following reason. Because you see, what is great about Aharonov-Bohm effect is that this is effect which you can do at large distances and which is completely insensitive to the mass of the gauge field. Now, the gauge field, the spin 2 that I was discussing, notice that the mass of that spin 2 doesn't enter anywhere, okay? It can be as heavy as the Planck mass. And nevertheless, the effect is detectable at large distances. Now, why? What's the reason for it? The reason for it is topology, because Aharonov-Bohm effect is a topological effect. It's completely insensitive to the mass of a photon, okay? It would be true for any mass of a photon. Of course, if photon is very heavy, then it will be hard to design the experiment in the lab. But the fact that you can detect it at large distances is completely insensitive to this statement, okay? So therefore, you can ask the following question. So therefore, in nature, this means that now if this is true, the fact that this mu can be non-zero. Now, unfortunately, from the point of view of low energy theory, it's impossible to say whether mu is zero or non-zero. We don't know, okay? So mu is some new quantum number, which high energy theory, our microscopic theory, endows a black hole with this quantum number. We don't know what it is. Then you can ask the following question. Suppose I watch my black hole evaporate, okay? So the end result of the black hole evaporations are particles. So what happens with this quantum number? Now, this quantum number cannot disappear. It's a topological number, this quantum Aharonov-Bohm here. So this means that it has to be transferred to a particle of a finite end product of the black hole evaporation, okay? So then the question is, and I don't know the answer to that question, can ordinary particles carry this mu, this quantum Aharonov-Bohm hair, okay, under this heavy gauge field? And well, from the point of view of low energy theory, the answer is yes. I mean, there is nothing that, no obstacle, fundamental obstacle, and it's measurable. So how would this manifest itself? This would manifest itself in the usual Aharonov-Bohm effect. Effectively, some particle which you normally would think that it's a neutral particle would exhibit the properties of the charge. Okay, so they will have some funny, tiny fractional charge. So from all the point of view, it will look like a charged particle. Okay, so which means that effectively it is becoming a charged particle because of this mu quantum hair. In a sense, you can also understand this as so-called Witten's effect, but okay, it's a bit involved to discuss. Okay, so now this discussion, as I said, I mean, I just used this spin 2 as an example. So this can be generalized to an arbitrary massive, arbitrary high spin, starting from spin 1, high spin massive gauge field. Okay. And so in each case, you can have a corresponding quantum number, this Aharonov-Bohm hair, which can be endowed. So the black holes can carry it, for sure. And then the question is whether particles can continue carrying it. And if they can, then you can detect them in laboratory. I don't know. There are all these experiments. Nina, I don't know if she will have time to talk about it. They were thinking about some interferometry experiments, which would be very sensitive to tiny tiny charges of the particles. I don't know. People are doing these experiments with neutron neutrality, for instance. That's another possibility. So this hair will show up as some kind of tiny charge. How much time do I have? 5 minutes? Okay. So now, in the remaining 5 minutes, let me just tell you another implication of this Aharonov-Bohm hair. The point is that actually it's not completely true. I told you that this mu is a fundamental parameter. Okay, it's like an electric charge. So there is some microscopic theory, and this theory tells us if a given black hole can carry it. If it cannot carry, if mu is 0, then there is no effect. I'm sorry. If mu is non-zero, we can detect it. Okay, at large distances. Now, however, this is not completely true that we don't know anything about mu. So in particular, we know that actually mu times q has to be quantized in units of 1 over n, okay? Where n is some integer number, and this n satisfies the following bound, that n has to be less than the Planck square divided by m star square, where m star square is a mass of a black hole or a particle with the smallest charge to mass difference, charge to mass ratio, okay? And now you can prove this by the following thought experiment, actually. I don't have time to go into much details, but you can prove it that actually if you imagine a black hole and we throw the n units of this quantum hair carrying charges, and then we wait for the black hole to evaporate, you are led to the proof that to the conclusion that that bound has to be satisfied. Otherwise, you are running into the conflict with either black hole thermality or the energy conservation. Okay, and so this tells you that you arrive to this bound. So the maximum n is this. So now you can turn this around. You can turn this argument around actually, and then so now I'm going to a speculative part. Okay. So you can turn this argument around and you can say, okay, this means that this scale m star and the quantum hair, they are correlated. Okay, so this means that if we postulate that there are particles with a tiny quantum hair, with a tiny number mu, then by consistency in these theories, the scale where gravity becomes strong has to be lowered. Okay, so there is this connection, and so I don't know. There are these ideas to use maybe this tiny quantum hair, particles with tiny quantum hair, for addressing the hierarchy problem. Now, the great thing about this is that in that case, the black holes, the smallest black holes available, they become very light. And so if you address the gauge hierarchy problem, the hierarchy problem in the standard model, by postulating this, that there is a particle with a tiny quantum hair, this implies that the lightest black holes can have TV mass. And so in this particular case, these are these black holes that people are talking, producing them at LHC experiments. At LHC, okay? All right, so let me conclude. Now there are two important messages. That the first one is that Aharonov-Bohm quantum hair, this gives a remarkable possibility to probe the short distance physics in large distance experiments, okay? And the reason is because it's topological. And because of its topological nature, the effect of this hair extends to infinity, because it extends beyond the Compton wavelength of a gauge field. And this is very important. Okay, so and then we can look in laboratory for this appearance of the seemingly charged particles with tiny charges, and that would be a signal of something like this. Okay, thank you very much. Of course, yeah. No, absolutely. There's no proof. But I mean, the fact that it may be non-zero and it's detectable, it's already remarkable, because we have this folklore about black holes. That black holes do not carry any information about their origin, etc. This tells you that those statements are purely classical. Quantum mechanically, Aharonov-Bohm effect can distinguish between different black holes. So you can have black holes with mu 0 and mu non-zero. And that's an observable effect at large distances. But, of course, I completely agree. So mu may or may not be 0. I mean, there are fundamental theories in which mu is predicted to be non-zero. And there are models in which, yeah.
You're talking about a phase shift.
Absolutely, it's an Aharonov-Bohm phase shift.
But what field does experience that phase shift? So,
what do you mean? This is a... Yeah, this is a part. So, of course, in the ideal example that I considered, I discussed it first. So, this is whoever carries this mu, the quantum here mu, behaves exactly as electrons behave in Aharonov-Bohm experiment.
So, okay.
These are these guys. Now, of course, for the classical black holes, so big classical black holes, the point is, for the big classical black holes, this is of academic importance.
So the phase shift is in the mu field, or?
No, mu is the charge. Mu is like a charge. What happens is that mu acts like a charge for a black hole. Okay? So, in other words,
sorry, so the black hole would experience that phase?
yeah, of course, yes. But for the classical black holes,
Interferences of black holes.
yes, but of course, that's what I'm saying. For the classical black holes, there is an effect. There is always an effect. But of course, for classical black holes, the effect is tiny, and you can never do that. You can never find a solenoid to lasso an astrophysical black hole anyway. So that's not the point. The point is that once these black holes evaporate, or the small quantum black holes, or any remnant of them, this quantum hair cannot disappear. It's endowed once and forever. So this means that some states in your theory, some quantum states, should be endowed by this quantum hair. And those can be anywhere. I mean, for instance, if you ask me, I mean, can an elementary particle can carry this mu, it's a tiny quantum hair? I don't have any fundamental reason why they cannot. Okay? So which means that, and in the experiment, this will show up as a tiny fractional shift of a charge. So you may be surprised. Now, but amazingly, for instance, we tried to understand in the previous experiments whether this would be already, you could already put some bound on mu from the existing Aharonov-Bohm experiments. And the point is that you cannot even. Why? Because usually when people are doing Aharonov-Bohm, suppose in Aharonov-Bohm experiment it appears like it, as if your electron charge got shifted. What you would do, you would attribute it to systematics, period. Right? You would say, okay, I don't care because I'm only looking at the differences. So here this would appear, for instance, as a tiny shift of an electron charge. That's one thing.
Maybe I missed something.
Yeah.
Because you conclude that we will discuss laboratory experiment.
Yeah.
What will play the role of black hole in laboratory experiment?
Any particle which is a remnant of the black hole evaporation. Any particle. So this tells you that if this tells you if mu is non-zero, this means that there are some perturbative states which finally get endowed by this mu. You cannot have something carried by the black hole and not carried by their remnants. Black holes evaporate. That's the point. So this means that then some elementary particles in your theory must be endowed by this quantum hair mu. No, everything is general. No, I disagree. No, look, I mean, the question, there are two different things. There is a matter of principle for the black holes, that this is an exception from the classical no-here theorem. Now, I could tell you the same about the electric charge. I mean, electric charge is not something you can predict. In the standard model, electric charges are inputs. This is why, because there is a microscopic theory, and that endows you with some electric charges. And that's it, right? The same is true about mu. All we are saying is that there is a new quantum number which is different, and it's there, and it will get transferred to particles, and is measurable in laboratory. And this will be inevitable signal of very short distance physics if it's measured. Yeah.
Okay, last short question.
You say that this is topological and the point could be seen on a very long distance.
Exactly.
But in fact, in reality, pretty much, Aharonov-Bohm, for instance, you can estimate that this can be seen on infinite distances because of the coherence effect.
Yeah, I mean, right.
Energies of the source of this fire.
No, this one can be literally seen at infinity. Why? Because this is a relativistic theory of a fundamental quantum Aharonov-Bohm hair. Okay. Now, the limitations in the usual laboratory experiments are because your materials are composite, and you have to do all the other effects are interfering. There are always some tails of van der Waals type tails, etc., etc. Those are technical. But the point is that the phase, once it exists, is topological. Topological numbers cannot change because they are either 0 or 1. They cannot go from 1 continuously to 0, right? So that's the reason.
It also adds to the dynamic of phase of the particle, and this can fluctuate, and eventually you will not see.
You're talking about technical problems, or you're talking about the technically, of course, always there is a problem. No, here no. This is a yeah.
Okay,
Thank
so
you.
let's thank Dr. Dvali again.